Last episode, we started a motor across the line. Full voltage, straight to the windings, 1 speed, and about 6 times the full load current on the way there. A variable frequency drive changes both of those. Any speed you want, and a start so gentle the inrush nearly disappears. And the whole thing rests on one equation you can write in a single line. An induction motor's speed is not set by voltage. It's set by frequency. Synchronous speed equals 120 times frequency divided by the number of poles. A 4-pole motor on 60 Hz. 120 times 60 is 7,200, divided by 4 is 1,800 RPM. Now change nothing but the frequency. Feed that same motor 30 Hz and you get 900 RPM. Half the frequency, half the speed. That is the entire idea behind a drive. One footnote. The rotor always runs a little slower than that rotating field because it needs the difference to induce any current at all. That gap is called slip. It's why a motor you'd call an 1800 RPM motor says 1750 on the nameplate. About 3%. So how does a drive make a frequency the power company isn't sending you? 3 stages. First, rectify. A diode bridge turns the incoming AC into DC. That's episode 26. Second, store it. Capacitors smooth that into a steady DC bus. Third, invert. A bank of fast electronic switches, IGBTs, close cousins of the transistor from episode 28. Chop that DC back into pulses. Vary the width of those pulses, and the motor sees whatever frequency and voltage you asked for. But you can't just change frequency and walk away. Here's the rule that keeps motors alive. The magnetic flux in the iron is proportional to voltage divided by frequency. Drop the frequency and hold the voltage, and that ratio climbs. Flux climbs with it, the iron saturates, and current goes through the roof. So the drive lowers the voltage right alongside the frequency. Volts per hertz held constant. Put numbers on it. A 460 volt motor at 60 hertz. 460 divided by 60 is 7.67 volts per hertz. So at 30 hertz, the drive gives it 7.67 times 30. 230 volts. Half the frequency, half the voltage, and the flux never moves. Now, the thing that actually burns motors up, and it's the most common complaint you will ever hear about drives. Run a standard motor slowly for a long time, and it cooks, not because of the electronics, because of the fan. That cooling fan is bolted to the shaft. Slow the motor to 30 Hz and the fan is turning half speed, moving roughly half the air. But a constant torque load still pulls near full current. So the motor is making just as much heat with half the cooling. Below about 30 Hz, that's a losing trade. The fix is an inverter duty motor or a separately powered blower. Going the other way has its own limit. Past 60 Hz, you can't raise the voltage any higher. You've run out of line. So volts per hertz starts falling. Flux falls, and torque falls with it. Below 60, you get constant torque. Above 60, roughly constant horsepower with fading torque. And here's the bonus that pays for the drive. Remember 6 times full load amps at start? A drive starts the motor at a low frequency and ramps up, so the rotor is never far behind the field. Starting current drops to something like 1.5 times full load, and the mechanical shock goes away with it. So, speed is 120 F over P. Volts per hertz stays constant to protect the flux, and a standard motor run slow is a motor with no cooling. Next time, back to the board. Grab a pencil, and I'll see you there.